Hello everyone. Today I'm going to give you a demo on solving heat transfer problems numerically by using ANSYS Fluent software. The heat transfer problem considered here is an enclosure containing water inside it and different boundary conditions applied along the walls of the enclosure as shown in the figure. The left wall is considered insulated. The bottom wall is kept at a constant temperature of 35 degrees C. The right wall is considered having a heat flux of 50 watts per meter square, and the top wall is considered open with a convection coefficient of 10 watts per meter square degree C. So the heat given into the system is from the right and bottom walls, and the heat carried away from the system is from the top. The temperature contours will be plotted at steady state condition for this study, and the results can be verified analytically using the heat transfer equations. So let's go on to start the ANSYS Fluent. First, I will go to the desktop button, go to ANSYS, then go to ANSYS Workbench. It takes a minute to start. So now this is uh, the workbench of ANSYS. Here you can see you can solve a variety of problems from coupled flows to fluid flows to vibration acoustic problems and transient structural thermal variety of different problems. Today I'm going to give a demo on ANSYS Fluent. So let's double click on that. So this tab will open up as soon as you click on ANSYS Fluent. So the workflow in this is first you create a geometry, then mesh the geometry, then set up the problem for simulation and solve it, and then get the results and analyze the results. So I'll go create a geometry first. I'll right click on it and then go to design modular geometry. So this opens up the design modular module. Um, so this is all the XY planes. So I'll go to the XY plane first. Right click and select look at. So it's quite a big domain here, so I'll just zoom in. The sides for the problem we are going to consider as a square enclosure with 10 centimeter per side. So uh, let's go to sketching, and then I'll create a rectangle uh, from origin to some point, and then I will go to dimensions to uh, specify the dimensions of the sides. So I'll select one and then select the other side. Then I'll go here and enter zero point 0.1 meters, which is 10 centimeter, and then press enter. And same for the other side. Okay, so you can see that our domain is created. So I will go to modeling. Then we need to create a surface from this sketch. So there is a command called surface from sketches. So I will go to concept, Then select surface from sketches. Here it will ask which surface, which sketch to select. So I will go to the XY plane, expand it, uh, select the sketch one, and then press apply, and then press generate over here. So it generates a surface for our problem. So I will exit the geometry as our geometry is created. One thing I should have done before is uh, go to properties, then that's okay. It doesn't show the. I wanted to create a uh, mention that it was a 2D analysis, but it doesn't show over here. So that's fine. I'll just go to meshing. Uh, once everything is created, you will get a green tick like this. So it tells us that you are ready to do the next step. So I'll go to meshing first. Next, double click on that. So it will open up the meshing module in this. Okay, that's our sketch. So we need to mesh this. So I'll go to mesh. I will specify the element size as 0.001. There are different methods you can use to mesh, but I'll go with the element size one and just generate. There are different methods you can mesh. So like you can divide the two sides into different number of elements and then mesh it. Or if you think that the physics is uh, more at some boundary, so you can uh, make the mesh finer at that boundary and then coarser where there is no effect of physics on the domain. So there is a variety of things you can do during meshing. So, but for this, I'll just keep it simple and do the regular element size mesh and keep the uniform mesh for this case. So you can see that it created a uniform mesh of uh, element size of 0.001 meters. So after the meshing is done, I will uh, give naming to the boundaries. So I'll select the geometry, um, then select the left boundary, right click on it, and select create name selection. So I will give a name as insulated, as this boundary is insulated. Enter. Then I will name the bottom boundary. Similar way, right click, press on create name selection. I will specify it as constant temperature. Then I will name the right boundary, create name selection. This boundary is constant heat flux, so I'll name it as constant heat flux. And the top boundary is convection. So I will name it as convection. Then I will name the surface. So I'll select body. Then I will select this body and right click. Then I will select create named selection, and I will select this as water, as our heat transfer fluid is water. So we are done with the pre-processing. We created the boundary. I mean, we created the domain, we created the mesh, and we specified all the boundaries. So now we'll close this tab and go for setting up our problem. So this one needs to be updated. So I will right click and press update so that we'll get a green tick as in geometry, uh, as you can see here. Okay, that's done. We got a green tick. So now we can head further to setting up the problem. So double click on that. It will show uh, a tab. So there are different options in this. So for more precise solution, you can select double precision, but it takes more time to solve for when you select double precision. Then you can use parallel computing. So this parallel computing is just for the local machine. So based on how many cores you have, you can select a number of cores over here. But I'll not do parallel computing for this problem, as this is a very simple problem. Then as you can see, it already took the problem as 2D, so we don't have to select anything over here. Uh, then I'll go start the setup. So this is the Fluent module, which computes the problem. So it loaded our geometry and the mesh. Um, so first thing we need to do is check the mesh and then report the quality. So if there is anything wrong with our mesh, it will show an error message over here. But this is good for now for us, and we can go ahead. I will select gravity in this case because there might be some convective currents inside the water. So I will select minus y because gravity will act in negative direction of y-axis. So I will select minus 9.81 in the y direction. Then we can go to the models. So for this condition, for this problem, we have to use the energy equation. Just double click on that and enable the energy equation. And for viscous conditions, we can use laminar condition. Double click on that and consider select laminar and OK. As you can see here, there are different uh, models which you can use from multi-phase, radiation, then heat exchanger, discrete phase modeling, solidification and melting modeling, and then you can use acoustics and structural also. Um, so there are a lot of capabilities for our ANSYS Fluent, as you can see here. So now we will go to defining the materials. Um, for the enclosure material, I'm going to consider it as a steel, and for fluid, I'll consider as water. So and I will double click on materials and then select create edit. There is a huge database of materials in Fluent. So I'll use the Fluent database for fluid and then select water liquid as our material. I'll copy it over there and then close it. And similarly for solid, for steel, I'll use the Fluent database for solids and use steel as the material for the enclosure. Copy it and then close. Then I will go to the cell zone conditions. Uh, Cell zone conditions is the interior water. So I'll give material as water to it and select apply, close. And for this, there are different things you can do. There is like source terms. If there is any source inside the domain, you can use that. There is porous medium. If also if your domain is a porous medium, you can use that. Then different other things like adaptive mesh and moving mesh or something. You can use that in this also. Then I will specify the boundary conditions for our problem. So as you can see, it took our boundary conditions which we specified earlier. So constant heat flux, constant temperature, convection, insulated, and then interior water. So I'll start with the first one, constant heat flux. Double click on that. Okay, so for momentum conditions, I will consider this no slip wall and stationary wall. And for thermal properties, I will give a heat flux of 50 watts per meter square, as we mentioned. And I will give the thickness of wall as 5 millimeters, so 0.05 meters. And I will change the material to steel. And I'll apply and close. Similarly, for constant temperature, I'll keep the momentum conditions as the default ones, no slip and stationary wall. And I will, oh, before I do that, you can change the units of different properties over here. So I will select uh, degrees C for temperature as the default value for temperature is Kelvin in ANSYS Fluent. So I will change it to degrees C. So just click on uh, degrees Celsius and it will select if it will offset by 273.15. You can see that there are different properties and you can use different, I mean, set units or different properties from this list. So I'll go on to set the boundary conditions of constant temperature. Um, so in thermal, you have to go for temperature, and I will give 35 degrees C as the constant temperature and select steel as the material and give wall thickness as 0.05 meters, which is 5 millimeters. Apply and then close. And for the top surface, there is convection. So uh, I will keep the momentum as default values, no slip, stationary wall, and I can give a convection heat transfer coefficient as I mentioned 10 watts per meter square Kelvin, and free stream temperature is 25 degrees C. There is no wall, so I'll give wall thickness as 0 as we consider the top surface as open. And I'll apply the material to steel and then apply these conditions and close. And for insulated wall, I will keep the default conditions for momentum, and heat flux at this wall is 0. So, but still I'll give the wall thickness as 0.05, 5 millimeters. So heat flux is 0, so the wall, there is no heat transfer across this wall. So that's why it's you can say it as insulated. Apply the material as steel and then apply and close. So next, I will head on to the solution methods. So in this pressure velocity coupling, I will use the method as simple for this problem and keep all others as default methods. So momentum is second order upwind, energy is second order upwind. So that's good. Then there are different values which you can use, like under relaxation factors. If your solution is not converging, then you'll have to use different values for this. But um, for simple problems, you don't have to play much with these values. So I'll keep those values as constant. I mean, the default values. And then I'll go to monitors. So uh, while calculating the solution, uh, there are some factors that you can plot or calculate while the simulation is still running. So the, from here you can set up those values which you need while the solution is running. But for this problem, it's a steady state, so we don't want to uh, calculate any values. So uh, this is the residuals. So this tells us how much accurate our solution is. So this is the currently this is set up for 1% accuracy. So I just want to increase the accuracy to 10 to the power minus 6. So I'll add two more zeros to continuity, x velocity, and y velocity uh, equations. And press OK. Then I'll go to initialization. So before we solve or calculate the problem, it has to be initialized. So the the computer should know what initial values we are going to give to the problem, so that it can start from there and then compute all the way to the final solution. So I will do a standard initialization. Then I will select compute from all zones and select the temperature as 25 degrees C, as that is the initial temperature. And then select initialize. So it will initialize the solution. And then I will go to run the calculation. So before we do the calculation, I will just check our case. So if there is any errors or if there is anything missing, it will show us some recommendations. So I'll just select check case. So it shows that there is no recommendations at this time. So our setup is good. And I will run this setup for 1,000 iterations. And reporting interval is 1 and the profile update interval is 1. So I'll keep that as default and press calculate. So now this is the convergence plot. Uh, so this is the accuracy, the residuals 10 to the power minus 3, and it's still decreasing. So our problem is converging. This will take some time, just a minute to complete, I guess. So we'll wait. Okay, so our calculation is now complete. So now I will go on to obtain the results in the form of temperature contours. Um, so in the results, you can go uh, expand the graphics part and select contours. So we need contours of temperature. So I will select temperature, static temperature, and I will select interior wall as interior water as where we want to get those temperature plots. So I will select save or display. And here you can see the plots of temperature. Um, then here is the graph of temperature. So it goes from almost 30 degrees to 35, 36 degrees C. So there are different things you can do color map option in color map options. So I will the number format here shown is exponential. So I will do general and then apply. So it will show us temperature from 30 to 36. And there are different things you can do, like align this plot along in the bottom right or top or something. And you can select precision also and select the font type. So I'll close this, and then you can name the different contours also. So I will name temperature contour and save display. And there are other things also you can get information from, such as if you want to plot uh, the data at certain points or certain uh, lines. So you can plot this XY data. If you want to plot temperature from, let's say, in the middle of temperature plot at the middle, so you can draw a line at the middle and then specify how many points are there on that line, and then you can plot the temperature along that line from top to bottom or bottom to top. And uh, there's a lot of things, other things also you can do. You can uh, uh, create animations, then use path lines or particle tracks for cases where the fluid is moving, like natural convection or uh, a fluid flow through a pipe, or other examples like that. And this uh, you can these results you can verify with analytical solutions uh, when you get the data from the plots, in this case. Um, so that's what I wanted to show you, how to set up and solve the problem in ANSYS Fluent. And uh, thank you.